distance between the robot and the cup, so degree when the robots move. The coordinate transformer is changed. The linear velocity and angular velocity change when the robots move. Hello everyone, welcome back to the Robot Starter Lab. In the previous video, we successfully detect the curve using our vision system and estimated its depth from the RGB camera. But detecting an object is only half of the problem. The next challenging is how do we make the robot actually move towards the curve? In today's video, I'm gonna explain the ROS2 pilot that make this happen. We go through 3 Python nodes: vision processor, coordinate transformer, and navigation client. By the end of this video, you are understanding how the robot converts a simple pixel location into real square robot motion. Let's start with the first node in our pipeline, the vision processor node. This node acts as the bridge between the RGB camera on the rest of our robotic system. Its main responsibility is to detect the curve in the RGB image, estimate its depth, and publish the information needed by the next node. The process begins with the RGB camera. Instead of continuously sending every frame to Google Colab, this node only sends an image when another node requests one. This greatly reduces unnecessary communication and improves the overall efficiency of the system. When an image is requested, the RGB codec resizes the image to 320 by 240 pixels and compresses into JPEG format. The compressed image is then public to the camera image compressed topic. In the Google Colab, we run our object detector, which can be either a simple SSV detector or a roller model. After detecting the curve, the detector returns only center pixel coordinates U and V. At this point, we know where the curve appears in the image, but we still don't know how far away it is. The cruise codec, that's where the coordinates codec come in. First is convert the RGB coordinate into the corresponding depth image coordinates, because the RGB and depth image usually have different resolution. Instead of reading only one depth pixel, the node search for a valid depth value slightly below the center of the curve. This is much more reliable because the lower part of the curve usually contain better depth measurement than the center, which may contain invalid pixel. After correction of valid depth value, the node computes a median depth using the median instead of a single measurement, makes the estimation much more robust against sensor noise and missing depth value. Finally, the nodes public 3 pairs of information: the image coordinates U and V together with the estimated depth. The value will be usually by the next node to compute the real-world position of the curve. Now, let's move to the second node, the coordinate transformation node. The previous node gave us the curve location in the image spaces. However, a robot cannot navigate using a pixel, which needs coordinate expressed in meter relative to the robot. The CameraInfo, the first input in the CameraInfo message. From this message, we obtain the intrinsic parameter of the depth camera, Fx, Fy, Cy. The intrinsic parameter requires the camera model are essential for converting image pixel into 3-dimensional coordinates. The curve detector, at the same time, this node receives the curve information produced by the previous notes the pixel coordinate and the depth value. Using the pinhole camera model, we convert the pixel coordinate into a 3-dimensional point inside the camera coordinate system. The rho is the cup position expressed as x, y, z relative to the camera. But the navigation system doesn't operate in the camera frame, it operates in the robot frame. Therefore, we use ROS2 TF to transform the point from the camera coordinate frame into the robot's frame. After the transformation, we public a point stamp message containing the cup position relative to the robot. This becomes the input for our navigation controller. Finally, we arrive at the navigation client node. This node receives the cup position in the robot frame and generates velocity command that drive the TurtleBot towards the target. Every time a new cup position is received, the robot reads true value x, which represents the forward distance, and y, which indicates how far the cup is from the center line of the robot. Linear P control. This forward motion is generated using a simple proportional controller. The farther the cup is, the further the robot moves. As the robot gets closer to the cup, it automatically slows down. Angular P control. At the same time, another proportional controller computes the angular velocity if the cup appears on the left on the robot turn left. If it appears on the right, robot turn right. This allows the robot to continuously face the target while moving. And I apply speed limit before publishing the command. I want to apply speed limit to pose the linear and angular velocity. This prevents certain movement and keep the robot's motion smooth and stable. We also introduce a simple but effectively strategy. If the cup is far away from the center of the robot, we temporarily stop moving forward and only rotate on the cup is approximately centered. The robot starts moving forward again. This significantly improves navigation stability. The finally velocity command is then published to the /TurtleBot /CMD velocity topic. TurtleBot receives the command and move towards the cup while continuously updating its motion based on new camera observation. And finally, the bot stop when the distance smaller than 0.3 meters. With the 3 cos Python, the vision processor, coordinate transformer, and finally navigation client nodes. Let's summarize the commit the pipeline. The vision processor detects the curve and estimates its depth. The coordinate transformer converts image coordinates into the robot's coordinates, and the navigation client compute velocity command and drive the robot towards the target. Together, the 3 ROS2 nodes from a commit perception to action pipeline. In the next video, I improve the system even further by adding obstacle avoidance and autonomous exploration, allowing the robot to search for cup even when they are outside the camera view. If you enjoy this tutorial, don't forget to like the video, subscribe to the Robot Starter Lab, and see you on the next one. Thank you so much.